Welcome to lesson 2, 7.3, solids of revolution. Okay, so the difference between this section and the last section is if I had you build things out of Play-Doh today, they would all basically look the same because they're all circular cross-sections. And the reason for that is we're taking shapes and we're revolving them in space, and whenever you turn something around in a circle, you get a circle. So the cross-sections aren't very interesting. They still, though, are the key to solving the problem. So the first thing I want to do is have you just find the blue area on this first figure. Okay, and I think the answer's right there on your page. Sorry about that. But why is it pi times, r squared minus r squared? Can you justify that real quick?
Okay, so what I'm saying is because you're looking for the area, it's the whole radius of the circle is the capital R, right? But then if you try to find just the shape, you're probably going to subtract the radius of the inside one.
Yeah, areas are additive, right? So the area of this total circle, pi r squared, you can subtract out the white circle in the middle, which is pi little r squared, and this gives you the area of the blue, right? So it's just convenient in mathematics to factor out the pi. We find that to be helpful, especially if this is going to be an integrand or something, part of your integral. You're going to want that pi pulled out, not just from the r squareds, but out of the entire integral. We'll put it way out front and save it for later, Okay, so that's kind of how that one works. And then lateral area of a cylinder is a slightly different idea. Lateral area of a cylinder is when you visualize a cylinder as made up of parts, right? So a cylinder is technically really just a rectangle that has been closed in, right, and capped off. So if you take a rectangle and roll it up, you've got yourself part of a cylinder. This is called the lateral portion or the lateral face of the cylinder. Okay? And the area of this thing is exactly the area that we started with, right? It's the same thing. So the surface, just the lateral surface of this is a rectangular area. So when you wrap it up, right, the length of the paper becomes the circumference of the base. So let's imagine unraveling this. Imagine taking our proverbial scissors. Here's our scissors. Imagine slicing. Oh, I drew that backwards. Oh well. There we go. Slicing along here and opening it up, what would it look like? You lay it all flat and you have a rectangle. Your red cut is right here. So that length is, of course, still h. But this length going downwards used to represent this distance going around, right? So that's 2 pi r, right? 2 pi r, that's circumference. So it's been a while since you maybe unraveled the cylinder, but the lateral surface of a cylinder is just what? What is this area here? 2 pi r times h. Yeah. Okay, so L is 2 pi r times h. And you might say, where's my r squared? You don't need it. You have centimeters times centimeters right here. So there's your square centimeters, r, h. Okay? So the first several problems will just use an area of a circle. We're not going to use either of these, okay? This is called a washer, and this is called a shell. Okay? We won't really need those until we get to one of the later examples. I forget which one. It turns out we probably need it until we get to example 5. Okay? In the meantime, we'll just do area of a circle, area of a circle, area of a circle. Okay, so let's look at our first example. Right here. And you have to visualize what would happen if... Where'd my solid go? Don't you guys have a picture right there? What is that? It's weird. It's really strange. I don't know what that's doing there. It reappeared. Okay, somehow that thing got pasted over with isometric paper. That's all right. There it is. We're going to be rotating this thing around the y-axis. Okay, the answer is going to come out to 6 pi, as we'll see here. So what I want you to do is just draw a little loop-de-doo. This is officially called the loop-de-doo. I drew it right here. It's the scientific name for it, loop-de-doo. It's spelled L-O-P-P-D-E-E-D-O-O. Loop-de-doo. L-O-O-P. Two O's, one P. Two O's, one P. Okay? All right. Loop-de-doo. Did everyone draw the loop-de-doo? I'm just kidding. I made up that word. Or I heard it somewhere. But what's going to happen is each point, not just on the edge of this, but each point, even on the interior of this, they're all going to wrap around, okay? You don't have to draw these dots. It's just kind of fun for me. Those are all going to rotate around the y-axis, okay? And each one's going to traverse a circle. And the radius of that circle will be the current distance for that point to the y-axis. For example, this point right here is probably the furthest point from the y-axis that we have, and it will travel along a large circle on its own loop-de-doo. That's loop-de-doo number one. Okay? And this point right here also would travel along its own loop-de-doo. How big is its circle? Depends on how far it is from the y-axis. Looks like it's going to follow this circle. See? And every point's going to do this, even the ones on the inside. They're all going to follow their loop-de-doo, and we're going to form a solid with a volume. So this blue area is going to sweep through space, forming a blue solid. So here is our blue solid, drawn in blue. This is the resulting solid. Does it look familiar? It's a cone. In fact, one of the definitions of a cone is the rotation of a line about a fixed point around a certain axis. So actually, if you look in your pre-calc book, in section 9.1, you'll see that a cone is defined as a rotated line. Anyway, the formula for surface area and volume, those are sort of givens in your geometry class, but there was no context for them. No one knew where they came from, right, except the people who created those formulas. So today we're not going to rely on formulas. If you do 1/3 pi r squared h right now, you'll get your answer. Watch, I'll show you. Volume is 1/3 pi r squared h. Maybe you remember this formula. The radius is clearly 3. The height is clearly 2. This gives me 1/3 times pi times 3 squared times 2. That's 6 pi. That's cheating. Okay? Why do we even believe that this is the right formula in the first place? Just because our geometry teacher said so? No, not a good reason. So, I was considering maybe drawing this in 3D, but I think it's 3D looking enough. So let's just get rid of the isometric here. You don't really need this in this lesson. I'm not going to use it much at all. Okay, so how would you treat this problem as a calculus problem, now that we kind of know the answer? What you do is you would ask, what's it made of? Well, it's made up of circles, right? Made up of circles. So let's take this particular loop-de-doo, and let's bring it out and draw it over here, and give it a little bit of thickness too. Give it a little bit of dy. Okay? This is a disk. That's the definition of a disk. It's got a little bit of thickness. Go ahead and label it a disk. How would you find the volume of such a disk? Base area times height. Same old, same old. So the volume, the differential volume would be base area. What kind of shape is the base? Circle. So pi r squared. And height. How tall is the shape? dy. This is your differential volume. Now all that remains is for you to figure out the r. So what is the radius? Well, the radius is the distance from the center to the lateral edge, right? So that's defined as radius. And in this picture that we started with, it was originally just our x, you see. Like it was just the x-coordinate of whichever point we did the loop-de-doo for. So that's just plain x. So we're sort of updating this. We're going to say it's pi x squared dy. But we still have a bit of a variable mismatch. We've got a dy and we've got this x going on. I would like to replace x with something that has y in it. Well, the expression was that x was 3y over 2. It's actually given in the diagram. Just got kind of covered up in my work. X is 3y over 2. Even if they had written that y is 2/3 x, I would have been able to interpret that x is 3y over 2. And that's going to get plugged in. So here's my differential in one variable. And this represents one of the many disk's volumes. So now I'll simply integrate. Integrating the left side gives me v. Integrating the right side gives me this integral, y squared. So I'm integrating. I've already squared the 3/2. I've already squared the y. I've already pulled the pi out. But I'm integrating this to collect them all, you see. Integrate means to combine or to sum them up, add them up. So this is going to be a very simple integram, and I just need limits of integration. So notice my first disk would actually be at the bottom. It's tiny, it's 0. Actually, it's very, very small, infinitesimally small. Tiny little disk is down here, down where y is 0. Then the disks stack this way until you reach the top. The top of this is clearly at y equals 2, you see. So you just look and see where the boundaries are on your dy. It goes 0 to 2, you can tell. And this just gives you 1/3 y cubed, evaluated between 0 and 2. Let's pursue it real quick. We have 9 pi over 4 out front, and we have 1/3 times 2 cubed minus 1/3 times 0 cubed, and this recovers that 6 pi. So forget the formulas you learned in geometry. Literally forget them all. Because all of them can be recovered with basic integration. And it's such a better way to learn it. It's really a shame that you can't learn this first and then learn geometry. But there's no way. Students' minds wouldn't be ready for the calculus. What a great concept, though. Okay, so that 1/3 that you saw in the 1/3 pi r squared h formula 4 years ago, where's it from? Where'd it come from? Integration. It's the antiderivative of y squared, 1/3 y cubed. That's where that 1/3 came from. And the 4/3 in the volume of a sphere formula comes from integration as well. Okay? So the Greeks, way back when they were studying geometry, they knew that the volume of a cone was 1/3 pi r squared h, but they didn't know where the 1/3 came from. They had some other harebrained way of explaining it. The integration shows us very, very clearly that it's a 1/3 and not a 1 over 2.99, So we'll just pursue the same logic on every problem. First we'll draw the loop-de-doos. Then we'll find the disk. We'll sketch the disk, write the dv, integrate it, and we're done. So let's look at number 2. This one has a strange answer, pi squared over 16. When was the last time you saw pi squared? Well, the reason is this one is very hard to integrate, even after you get it all set up. Okay? So it's going to require 2 trig identities to solve it. It's going to be tough. First thing we notice is it's revolved around the what? The x-axis. So let's draw at least 1 or 2 loop-de-doos. Okay? Here's your general loop-de-doo. This guy's going to follow loop-de-doo. This guy's going to follow its own loop-de-doo. He's the biggest one. Okay, so the blue solid looks like something that happened, that was being used on TV Sunday. What does this thing look like? Football. Looks kind of like football, right? Super Bowl. It's like a cartoon football. It's really exaggerated. But can you picture it as a solid? If you can't, just draw more loop-de-doos. Okay? So there it is. Some kind of a weird football thing. And we'd like to find the volume. Okay, so let's draw one disk. That's sort of my strategy. Just pick one disk, pull it out, analyze it to death, and we're ready to integrate. So let's draw this one. Pull that guy out. Give it a little thickness. By the way, some teachers don't teach it as a disk. They think of it more as a area integrated through space. So I'm giving it thickness now and imagining collapsing that. It's a little bit different philosophy, but whatever leads you to the answer is fine. So here is your cylinder. Did you have a question? Okay, we know that the volume of a cylinder is base area times height. Notice it's standing on its edge like that coin was when it was rolling across the floor a minute ago. Okay? It's rolling along its edge. And the dV is going to be base area times thickness or height. So base area is obviously pi r squared, no big deal. Height is what? Be careful here. It's not dy this time. What is it? dx. Notice that the thicknesses lie in the x direction. They are horizontal thicknesses. So this is dx this time. So by height, what we mean is thickness. Thickness. So if it was laying flat, it would be its height. All right. It would be nice if the r was written in terms of x, because this is going to become our integrand in the moment. We don't want to have r and x going on at the same time. So now this is where you kind of come back to the picture and you ask, okay, what does the r represent in my picture? And the r represents a y value. You can see it's vertically drawn, right? So yeah, it's basically the function they gave you. The bottom of it's at 0. The top of it's right on the curve, the blue curve. So in a very real sense, that radius is always sine x cos x. And that gets substituted in. So dv then becomes pi times sine x cos x squared dx. And if you just slap an integral on both sides, you've got v on the left, and you've got an expression to solve on the right. So we're going to treat the integral symbol as an operator. We just throw it in whenever we want, as long as it's a differential. So just go like that, and you're ready to go. So the left side is v. The right side is going to give us a headache. Okay? Before we start this integration, I think we should ask what the limits of integration are. So you have to ask, where are the disks? They all live between where and where? Obviously, they all live between x equals 0 and this point over here. Right? So where is this? This is a very important question. They didn't say, but we should be able to figure that out. Yeah. But we have a contest here between sine and cosine. They both give us different zeros, right? But this is the very first zero of the function, you can tell. And cosine of pi over 2 is 0. Sine doesn't become 0 until we reach pi. So we have to go with the first root we can think of, the smallest one we can think of, and it's just pi over 2. So this is actually pi over 2 right here. The function will zero out when it hits pi over 2. So if this is a pre-calc classroom, I would have to spend 15 minutes explaining that. But the first root of y equals sine x cos x should be pi over 2. Okay, so that's your limit of integration, upper limit. That doesn't make the integral any easier to solve. So what I would do on this problem is get out another piece of paper, so you can just do all your integration there, and then you could transfer the answer over, the antiderivative. Okay, so that's what I need to do too. There's just not enough room on here at all. Okay. Okay, so we're going to be doing this integral, and we have an awkward integrand, sine squared cos squared. Okay? So there's an identity that can come to our rescue, and that is this one. Cosine of 2x equals 2 cosine squared x minus 1. Remember this identity? If you're in calculus, you might not remember this one, but it is a pretty important one. Okay, it's a double angle identity for cosine, and it actually has another version, cosine 2x equals 1 minus 2 sine squared. So these guys are going to come to our rescue. If you isolate the first one for cos squared, you'll get a nice replacement for cos squared. If you isolate sine squared in the second one, you'll get a replacement for sine squared. So it turns out you can actually replace the sine squared with 1/2 minus 1/2 cos 2x. And you can replace the cos squared with 1/2 plus 1/2 cos 2x. This is very powerful because it just took quadratic trig expressions and turned them into linear ones. That's awesome. That means we don't have any cosine squares anywhere, well, until we FOIL. But we would have had a cosine to the, like a cosine to the fourth if we had used Malma's theorem or something. That's no good. Okay, so you can see that each of these parentheses, you could pull out a half. So I'm going to pull out a half twice, which puts a 1/4 in the very, very front. So I like to call that the front. So way out in the front, I have a pi over 4 now, and inside I have a 1 minus cos 2x times a 1 plus cos 2x, which I need to FOIL if I'm going to solve it my way here. So you could probably use parts by now, but I'm going to go ahead and FOIL it. This gives me 1 minus cos squared 2x. Okay, is there an identity for cos squared 2x? Well, let's just do this by analogy. If cosine 2x is to cos squared x minus 1, then isn't it true that cosine, I'm sorry, what I meant to say was if cosine squared x can be replaced with 1/2 plus 1/2 cos 2x, couldn't cosine squared 2x be replaced with 1/2 plus 1/2 cosine 4x? Just by analogy alone. There's no reason why we couldn't change x to 2x and write this identity this way. Okay, so I'm going to replace this only with that. And then we'll be ready to integrate it. It'll be easy. So pi over 4, this is 0 and 2. I've got a big fat 1 here minus. I'm planning on replacing that garbage. That cos squared 2x, I'm replacing that with 1/2 plus 1/2 cos 4x. All right, and then I'm going to erase some of my side work so I have some more space, because I'm running out of room again. All right, so let's bring this over to here. So I have the pi over 4 chilling out front. This should have been a pi over 2 upper limit, not pi. There's a 1 minus a half there. No big deal, that's a half. And then I have a minus 1/2 cos 4x. And now this is completely linear, like it's one cosine function. It's so easy to integrate now. We're very grateful for the identities. So we have pi over 4. The first term integrates to 1/2 x. The next integrates to 1/8 sine 4x. Lower limit, upper limit, plug them in. Finally. So we have pi over 4, and then our first term is 1/2 of pi over 2, so that's also pi over 4, minus, and I'm distributing this onto the f of a and f of b here. And then we plug in these, I shouldn't distribute quite yet. Let me hold off 1 second. It's going to be pi over 4 minus, what's 1/8 of sine of 4 times pi over 2? I think that's just 0. Yeah, if you plug in pi over 2 here, you're going to get sine 2 pi, which fortunately is 0. So that vanishes. So it's just the pi over 4. When you plug in 0, both these are gone. So actually we're done. This is completely done. The answer is pi squared over 16 as promised. Wow, that is a tough ending to a problem. And it's not really my focus today anyway. My focus today was to show you how to sketch the disk, write the dv, and integrate. It just took us a while to finish that integral. Okay, so this comes out to pi squared over 16 cubic units. That one's like borderline calculator problem. Okay? In fact, if you have to use the calculator, fine. You can work on your integrals later. But today we're trying to get that pi r squared set up. All right, let's go on to the next one. And you can work ahead if you want. This was a lot easier, I assure you. But you just have to sketch your own picture completely. So x cubed, y equals 0, x equals 2, revolving around the x-axis. Okay, so what I did on this problem was I made this direction, this is x equals 1, and this is x equals 2. That's what I did. And then for the y-axis, I went ahead and made these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on the y-axis and the x-axis, I have different scales, but it makes it a little bit easier to display my work. And we know that the y equals x cubed curve passes through 0, 0, 1, 1, and 2, 8. So it looks like that. That's y equals x cubed. Y equals 0 is another way of saying the x-axis. X equals 2 is a vertical line. So we're bound between here, basically. So this region here is what we're talking about. And we're planning on spinning this thing around over the x-axis. So we get to draw some loop-de-doos. Okay, let's draw some loop-de-doos. We're going to be going around the x-axis. It says right here, about the x-axis. Okay, so I'll give you a minute to draw the loop-de-doos. Draw a few so you can kind of feel the shape. What's that thing going to look like? And ask yourself what everyday object looks like. What kind of object might that look like? What's that? Okay, so a couple loop-de-doos can help you visualize it. Here's a loop-de-doo. Here's a loop-de-doo. Here's a big loop-de-doo. My second loop-de-doo wasn't big enough. Is this kind of what you drew? I don't know. Then think of an object that this resembles to help you remember. So what, I don't know, what does it look like? A horn, yeah. Maybe like the opening of a trumpet or something. But we would like to find the volume of it, or since I'm always thinking about chocolate or skateboarding pretty much all the time, I would just look at this as a Hershey's Kiss. It's a Hershey's Kiss. See?
What does that have to do with skateboarding?
It's just skateboarding and chocolate. It's like the two things my mind is on most of the day.
So skateboard. Did you see that picture? I'm sorry.
Check Hunter's Twitter account. Okay, so this is our Hershey's Kiss. We want to find the volume of it, but we really want to visualize the discs. So let's draw one disc in here, like that, and even pull it out so we can really analyze its depth. So like always, it's base area times height. Dx or dy on this one, look at the way these are pointing in space. These are clearly horizontal widths to these disks, so we're going to go with dx. Make sure you write that differential. It's super important, right? Which means I'd like to get my r now, and the r is measured the r is measured basically from the center to the top of each disk. So it varies as you go along, but it's clearly the y-coordinates of these points. So if you draw a couple radii, you realize, hey, wait a minute, this is just y equals x cubed is the length of each radius. So that's going to make a really simple integral. I'm just going to replace r with x cubed, see? So my dv is just going to be pi r squared dx. So your differential volume is pi x to the sixth dx, and this is really easy to integrate. Now you can see why there's a 1/7 in the answer, right? All right, so if you integrate the left side, you get v. If you integrate the right side, you're doing that between 0 and 2. You can leave the pi out front, but there is an x to the 6th here. So you basically get pi, I wrote x. I meant to write pi over 7 x to the 7th, evaluated between 0 and 2. And this is where you're going to get your 128 from. 128. Okay, x to the 7th is 128. So the answer is volume equals 128 pi over 7. Cubic units. Not too hard. Okay, so the next question asks basically, what happens if you're not rotating around an axis? What if you're rotating around some other line? So that's what this next one's about. Look at number 4. Find the volume of the solid generated by revolving the region around the given line. So notice it doesn't say around the x-axis anymore. So they're going to try and mess with us. Let's search the paragraph first for the line that we're going to rotate around. So if you read carefully on this, it talks about a region bounded above by this and below by that, and between 0 and pi over 2, and it's on the left, it's got the y-axis, and then right here, about the line y equals 2. That's very important. That's our rotation line. So let's draw that in right away. Complete with loop-de-doo. Okay, so I was just hunting for that. I needed that. I got to know what I'm revolving around before I even sketch. Okay, now I'll sketch it. Let's see. Evidently, this region is in the first quadrant. It says so. It says that it is bounded above by y equals 2. Last year, my students didn't understand that. They thought that it meant that it's drawn above y equals 2. No, it's bounded above by. It's a passive statement. So it's trapped under. Bounded above by means you're trapped under the line. Really, it's important. People were getting this wrong and they didn't know how to read it. So if something is bounded above by something, it means that they're trapped under it. If you're bound above by it, it's a passive statement. So you have y equals 2 as an upper boundary, you see. And then it's bounded below by the curve 2 sine x. Maybe we should draw 2 sine x. That just has an amplitude 2. It goes through, pi and 2 pi on the x-axis. Why don't we just draw it like this? We'll draw this as our pi, and this as 2 pi, like that. And we'll draw our curve coming up, and back down, and back up, like that. Okay, so we're getting there. The region we're talking about is bounded underneath the y equals 2 line, but above this line. And it is all between 0 and pi over 2. So I think we're only talking about this tiny little area here. You see? Just that. That's it. So I'm going to resketch. Here's y equals 2 sine x. Here's y equals 2. And this is between 0 and pi over 2, as drawn. Okay, so that was a lot of work just getting that figured out. And now we're going to be spinning it around the y equals 2 line. So it's going to form that trumpet look again, the bell of a trumpet. But it's not centered on the y-axis anymore. It's rotating around this line, the y equals 2 line. You see? Okay, so once you kind of figure that out, you can draw the disks, write down the differential volume, and integrate. So let's draw one disk. For the differential volume, pi r squared. Should I go with dx or dy? Look at the direction that the width is in. Dx, right? And here's where we have to be really careful. The radius is clearly vertical, but it isn't measured from the x-axis anymore. So this r corresponds to the distance between the top blue line and the bottom curve. So it's like that u of x minus L of x thing we learned in chapter 7 too. So I'm going to draw one radius over here. This is a radius. You see? That's a radius standing upright. And the topmost value of y is 2. And the bottommost value of y is 2 sine x. So how long is this little vertical segment?
2 minus 2 sine x.
Yeah, upper curve minus lower curve. All right. So that becomes the radius of the disk, you see. So r is going to have to be replaced with upper curve minus lower curve. That's tricky. So let's put that in. The rest will be easy. The r is the hardest thing to figure out. Everything's circular, but that's the hard thing. It's just 2 minus 2 sine x. And then that is quantity squared. And then you throw the integral on both sides. We're integrating from 0 to pi over 2. Okay, this one's not as bad as number 2 was, but it's still pretty ugly. And we do end up getting 3 pi squared minus 8 pi for a final answer. 3 pi squared minus 8 pi. Okay, so I'll write the integral. If this was a calculator problem, as you know, all you would need to do is write this. Bust out the calculator and type it in. And as long as you have the integral written properly, with correct limits of integration, and pi is there, and everything's there, there's your power squared dx, you're going to get full credit. Integral, answer, done, full credit. If it's a calculator problem. And of course, you'd have a decimal there. I think this is a good stopping point, because the next problem involves an object with a hole punched in the middle, and it's not necessarily harder, but it involves washers and not disks. So after tomorrow's lesson, you'll be comfortable integrating anything to find volume, as long as you know the functions.